Today we will going to discuss about an upper bound for a complex integral. First is statement of the theorem. If a function fz is continuous on a contour L of length small l, and if M is the upper bound of fz on L, that is mod fz is less than equal to m on L, then integral over L fz dz modulus is less than equal to m into L. That means your fz is a continuous function on a contour L of length L. M is the upper bound of this function. Then modulus of the integral fz dz over the arc L is less than equal to its upper bound and length L of the rectifiable arc L. Next proof. Let fz be a function of complex variable z defined and continuous at each point of the arc L, where L is the rectifiable curve defined by z equal to zt equal to xt plus iyt, where t lies between a and b. For different value of t in the interval ab, we will get different value of this z, and this z will represent a rectifiable curve L, that is different point of z will give the rectifiable arc L, and fz is a function of complex variable z defined and continuous at this point of this arc L. Let p equal to a t naught t1 tn equal to b any partition of AB. Okay. Then from the sum we have discussed this in the rectifiable curve lecture and complex integral formal definition of complex integral. You should go through this lecture and check out this sum k to the power n zk minus zk minus 1. Okay, we have already discussed this. This is not modulus, this is bracket. this is bracket f of chi k, where chi k is any point, where chi k is any point in the arc L, in the arc L. Okay. Now take modulus both sides. We will get Sn is equal to k ranges from 1 to n zk minus zk minus 1. This is k minus 1 above chi k. If I expand this, I will get this one z1 minus z naught. Put bracket here f of psi 1 modulus close. Then again z2 minus z1 f of chi 2 plus dot 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 zn minus zn minus 1 f of xn. Then again using the property of modulus, I can write this one z1 z minus z naught f of chi 1. This is by using this property of modulus less than equal to a. This. If you use this property, you will get this one plus z2 minus z1 above chi 2 dot plus dot 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 plus zn minus zn minus 1 f of chi. In the summation notation, we can write this one as k ranges from 1 to n zk minus zk minus 1 f of chi k. Okay, since modulus fz is less than equal to m on L, so in the next line it will be less than equal to m sin k over 1 to n zk minus zk minus 1 zk minus zk minus 1. This is modulus bracket. Now taking limit n tends to infinity, limit n tends to infinity, we get limit n tends to infinity Sn less than equal to sum over limit m limit n tends to infinity m sum over k from 1 to n zk minus zk minus 1. Since modulus is a continuous function, so we can take the limit inside the modulus. M, since m is constant, can be taken outside the limit and tends to infinity. K ranges from 1 to n zk minus zk minus 1. And this, by definition of complex integral as a limit of sum, we will get this as modulus of L f of z dz. You should kindly go to the lecture of complex integral as a limit of sum. That is formal definition of complex integral. You should go to the lecture. You will get it, which is less than equal to m. Again, this is integral L dz. You will get this, how this is equal to this one in the example of complex integral. This one, integral dz, and this there you will find it as this is from the example of complex integral, that is integral dz over the arc L is length of this arc L. Okay, here this is from the definition of the integral as limit of sum. Hence the proof. With that, I would like to conclude. Remaining will be in the next lecture. Thank you.